This is SpaceTime Series 28, Episode 8, for broadcast on the 17th of January 2025. Coming up on SpaceTime, finally the discovery of the origins of fast radio bursts, the link between lunar water and Earth's early history, and NASA's Juno mission uncovers the heart of the Jovian moon Io's volcanic rage. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have finally narrowed down the source of those mysterious fast radio bursts, or at least one of them, discovering that it really did originate around a rapidly spinning highly magnetic neutron star known as a magnetar. Fast radio bursts are sudden high-energy flashes at very specific wavelengths lasting just a nanosecond or two and originating at cosmic distances. But in that short space of time, they can release more energy than 500 million suns. The very first fast radio burst was discovered back in 2007 in data from the Parkes Radio Telescope in New South Wales. At first, most were singular events, occurring just once at a specific location and then never again. And that suggested they were probably being caused by some sort of cataclysmic event, such as a supernova. But astronomers are now detecting more and more fast radio bursts that have repeated from the same location. That suggests a very different cause. Feeding black holes, glitching neutron stars and highly magnetized neutron stars called magnetars have all been suspected. And it could be, in fact, that all fast radio bursts are repeaters, just that some are a lot more active than others. Now a report in the journal Nature has pinned down the origins of at least one fast radio burst using a novel technique that could be used to find the origins of more. The study's authors focused on FRB 2022-1022A, a previously discovered fast radio burst that was detected in a galaxy about 200 million light-years away. They were able to zero in further, more precisely, to determine the exact location of the radio signal by analysing its scintillation, similar to how stars twinkle in the night sky. The authors studied changes in the fast radio burst's brightness and determined that the burst must have originated in the immediate vicinity of its source, rather than much further out as some models predicted. The team estimates that FRB 2022-1022A erupted in a region that's extremely close to a rotating neutron star, 10,000 kilometres away at most. Now that's less than the distance between New York and Singapore, and at such close range, it means the burst probably emerged from the neutron star's magnetosphere, a highly magnetic region immediately surrounding the ultra-compact object. The study's lead author Kenzie Nemo says that in such environments of neutron stars, the magnetic fields are really at the limits of what the universe can produce. In fact, there's been a lot of debate about whether such a bright radio emission could even escape from such an extreme plasma environment. You see, atoms can't really exist around these highly magnetic neutron stars. They'd simply be torn apart by the magnetic fields. But it seems that the energy stored in these magnetic fields, close to the source, is twisting and reconfiguring in such a way that it can be released as radio waves visible halfway across the universe. Detections of fast radio bursts have ramped up a lot in recent years, mostly due to the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. This is a radio telescope array comprising 4 large stationary receivers, each shaped like a half pipe and tuned to detect radio emissions within a range that's highly sensitive to fast radio bursts. Since 2020, CHIME's detected thousands of fast radio bursts from all over the sky. While scientists generally agree that the bursts arise from extremely compact objects, the exact physics driving them remains unclear. Some models predict that they should come from the turbulent magnetosphere immediately surrounding the compact object, while others predict that the burst should originate much further out, as part of a shock wave propagating out from the central object. So, to distinguish between the two hypotheses and determine exactly where fast radio bursts arise, the authors considered the idea of scintillation, the effect that occurs when light from a small bright source such as a star filters through some sort of a medium, such as a galaxy's gas. We see the same thing happening here on Earth. As starlight features through the gas of the atmosphere, it bends it in ways that make the star appear to twinkle. And the smaller or further away the object is, the more it twinkles. That's why light from larger, closer objects such as planets experience less bending and therefore don't appear to twinkle. The authors reasoned that if they could estimate the degree to which a fast radio burst scintillates, they could determine the relative size of the region from where it originated. The smaller the region, the closer the burst must be to its source, and the more likely it is to have come from a magnetically turbulent environment. On the other hand, the larger the region, the further away the burst would be, giving more support to the idea that fast radio bursts stem from far-out shock waves. To test their hypothesis, the researchers looked at FRB 2022-1022A. That's a fast radio burst first detected by CHIME in 2022. The signal lasted about 2 milliseconds and was a relatively run-of-the-mill fast radio burst in terms of its brightness. However, scientists at McGill University found that FRB 2022-1022A exhibited one outstanding property. The light from the burst was highly polarized, with the angle of polarization tracing a smooth S-shaped curve. Now, this pattern is interpreted as evidence that the fast radio burst emission site is rotating, a characteristic previously observed in pulsars, highly magnetized rotating neutron stars. So, if FRB 2022-1022A originated from close to a neutron star, the authors should be able to prove this using scintillation. Nemo and colleagues analysed data from CHIME, observing steep variations in brightness which signals scintillation. In other words, the fast radio burst was twinkling. That means the authors had confirmed that there was gas somewhere between the telescope and the fast radio burst that was bending and filtering the radio waves. They then determined where this gas was located, confirming that the gas within the fast radio burst's host galaxy was responsible for some of the scintillation. The gas acted as a sort of natural lens, allowing the researchers to zoom in on the fast radio burst site and determine that the burst originated from an extremely small region, estimated to be just around 10,000 kilometres wide. Nemo says that means the FRB is probably within hundreds of thousands of kilometres from the source, and on cosmic scales, that's extremely close. Now, for comparison, one would expect the signal would be far more than tens of millions of kilometres away were it to originate from a shock wave, and under those conditions you wouldn't see any scintillation. In other words, the results clearly rule out the possibility that FRB 2022-1022A emerged from the outskirts of a compact object. Instead, the study proves for the first time that this fast radio burst originated from very close to a neutron star. This is SpaceTime. Still to come, the link between lunar water and Earth's early history, and NASA's Juno mission uncovers the heart of the Jovi moon Io's volcanic rage. All that and more still to come on SpaceTime. A new study has shown that much of the moon's water actually originated on the early proto-Earth. The findings, reported in the Journal The Proceedings of the National Academy of Sciences, analysed water in 9 samples from the Apollo-era lunar missions using a high-precision triple-oxygen isotope technique. The method separates water into its various binding phases, loosely bound, tightly bound, and trapped within minerals. It does this through stepwise heating at 50 degrees Celsius, 150 degrees Celsius, and at 1000 degrees Celsius. One of the study's authors, Maxwell Feymans from the Verger University in Brussels, says the data provides crucial evidence that lunar water had a dual heritage, one part originating from early Earth-like material and another derived through cometary impacts. He says it's a major step forward in unravelling where lunar water comes from. The findings suggest that the Moon inherited water tracing back to Earth's formation, followed by later contributions from comet impacts, delivering the water reservoirs we see today. The Earth-Moon system was created when a Mars-sized planet, which we now call Theia, slammed into the early proto-Earth some 4.5 billion years ago, causing both bodies to melt into a magma ocean. Now eventually this all cooled and coalesced to form the Earth as we have it today, and some of the debris ejecta flung into orbit around the Earth from the newly created planet eventually accreted to form the Moon sometime later. The study shows that the oxygen isotopic composition closely matches enstatite chondrites, a meteorite type believed to be one of the building blocks of the Earth. But there are also clear signs of cometary contribution, with a significant portion of lunar water showing isotopic similarities to comets. Interestingly, the findings also challenge the idea that the majority of lunar water was produced through solar interactions with lunar silicates, instead presenting a far more complex mixing of sources. This is SpaceTime. Still to come, NASA's Juno mission uncovers the heart of the Jovian moon Io's volcanic rage, and later in the science report, a study looks at the sorts of illnesses Disney princesses would have suffered were they real people. You can tell we're in the silly season. All that and more still to come on SpaceTime. Scientists with NASA's Juno mission to Jupiter have discovered that the volcanoes on Jupiter's moon Io are each likely to be powered by their own chamber of rolling hot magma rather than a single subsurface magma ocean. The new findings, reported in the journal Nature, solves a 44-year-old mystery about the subsurface origins of the moon's most demonstrative geological features. About the same size as the Earth's moon, Io is known as the most volcanically active body in our solar system. It's home to an estimated 400 volcanoes, blasting lava and plumes in seemingly continuous eruptions. In fact, if you could live on Io, you wouldn't have weather reports, you'd have geological reports, with mountain building in the north and lava lakes forming in the east. Io was discovered by Galileo Galilei in 1610, but it wasn't until the Voyager 1 flyby in 1979 that imaging scientist Linda Morabito from NASA's Jet Propulsion Laboratory in Pasadena, California, first identified a volcanic plume erupting from the surface of Io in an image taken by the spacecraft. Juno principal investigator Scott Bolton from the Southwest Research Institute in San Antonio, Texas, says since Morabito's discovery, planetary scientists have been wondering about how the volcanoes are being fed from lava underneath the surface. Were there shallow oceans of white-hot magma fueling the volcanoes, or were their sources far more localized? Scientists knew that data from Juno's two very close flybys of Io could give fresh insights on how this tortured little moon actually worked. The Juno spacecraft made extremely close flybys of Io in December 2023 and February 2024, getting to within 1,500 kilometres of its pizza-faced surface. During these close approaches, Juno communicated with NASA's Deep Space Communications Network, acquiring high-precision dual-frequency Doppler data, which was then used to measure Io's gravity by tracking how it affected the spacecraft's acceleration. What the mission learned about the moon's gravity from these flybys revealed lots of details about a phenomenon known as gravitational tidal flexing. See, Io is extremely close to the mammoth Jupiter, the largest planet in our solar system, and its elliptical orbit swings it around the gas giant once every 42.5 hours. As this distance varies, so too does Jupiter's gravitational pull on the moon, which causes the moon to be relentlessly pulled and squeezed. The result is an extreme case of gravitational tidal flexing, friction from tidal forces generating internal heat. Bolton says this constant flexing creates immense energy, which literally melts portions of Io's interior. Now, if Io had a global magma ocean, Bolton knew that the signal of its tidal deformation would be much larger than a more rigid, mostly solid interior. So, depending on the results of Juno's probing of Io's gravity field, Bolton and colleagues were able to tell if a global magma ocean was indeed hiding beneath its surface. The Juno team compared Doppler data from their two flybys with observations from the agency's previous missions to the Jovian system and from ground-based telescopes. And they found that the tidal deformation was consistent with Io not having a shallow global magma ocean. Juno's discovery that tidal forces don't always create global magma oceans has implications for science's understanding of other moons too, including Enceladus and Europa, and even exoplanets and super-Earths. One of the teams involved with the Juno mission are with the University of Leicester.
The objectives of the Juno mission are threefold. There is a study of the internal structure of the planet, how the mass is distributed on the inside, whether there is a solid core or not. Secondly, there is an objective to look deep within the atmosphere of the planet, above the visible cloud tops that you can see from Earth, to understand the structure of the weather layers beneath the cloud tops, the origin of the Great Red Spot and so forth. And thirdly, there is the objective of looking at the origins of the planet's auroras, which are the most intense auroras in the solar system. The Earth, of course, has auroras around the pole, so does Saturn, and so does Jupiter, but Jupiter is by far the most powerful. And we want to know the origin, the physical origin that drives the auroras, and the connection with the magnetic field at large distances.
The University of Leicester's involvement in the mission is through Professor Stan Cowley, who is a science co-investigator on the main Juno science team.
And that was because we had been involved in theoretical studies of Jupiter's environment in the immediate couple of years beforehand, and had produced a research paper that was published in 2001, which has become the definitive model of how Jupiter's auroras, or how we think Jupiter's auroras, are actually generated. And so when this mission was being proposed to NASA, we were the go-to people to be involved in the planning of the mission.
If we want to understand the solar system and how it formed, how it evolved over time, then we need to understand Jupiter. We understand quite a lot about Jupiter, but we don't know the details of the interior, whether or not it has a core, how much water is contained in the atmosphere. So the details are really, really important. And due to Juno's unique polar orbit, we really have an opportunity for a step change in our knowledge. It is a game changer. The results that will come from the Juno mission will significantly enhance our knowledge of Jupiter overall.
And in that report from the University of Leicester, we heard from Professors Emma Brunst and Stan Cowley. This is Space Time. And time now to take another brief look at some of the other stories making news in science this week with a science report. There now seems to be more carbon stored in human-made stuff on the planet than what there is carbon in the natural world. The findings, reported in the journal Cell Report Sustainability, looked at how much carbon is stored in long-lasting products such as plastics and buildings. The authors looked at the amount of fossil carbon in the technosphere, that's the sum of all human-made artefacts both in use and discarded. They estimate that some 8.4 billion tonnes of fossil carbon has been accumulated in the past 25 years, with approximately 0.4 billion tonnes being added annually. The authors say this has a huge potential to add to greenhouse gas emissions if the carbon locked up in these everyday objects were ever to be released. Researchers have shown that the expected lifespan of a dementia patient after they've been diagnosed varies dramatically depending on how old they are, their gender, and what type of disease they have. A report in the British Medical Journal combined results from 261 studies, predominantly from Europe and North America, looking at the lifespan of dementia patients. The authors say life expectancy varies greatly depending on the situation, with women diagnosed around 60 likely to live another 8.9 years, while men diagnosed in the mid-80s have an average life expectancy of just 2.2 years. Overall, researchers say dementia reduced life expectancy by about 2 years for people with a diagnosis at age 85, 3 to 4 years with a diagnosis at age 80, and up to 13 years with a diagnosis at age 65. 13% of people were admitted to a nursing home in the first year after their diagnosis, increasing to a third at 3 years and 57% at 5 years. Well, here's a study that proves we're now in what journalists call the silly season. The study has shown how, had they been real, each of the Disney fairy tale princesses could have exposed themselves to all sorts of harmful substances and illnesses, at least according to their storylines. The findings, reported in the British Medical Journal, show that Snow White, for example, would have been at risk of heart disease and mental health issues for her time locked away in a castle, and the long-term lasting effects of eating a poisoned apple should also be considered. Jasmine and Belle's proximity to large animals could put them at risk of all sorts of animal-borne diseases. Cinderella's exposure to dust and magical glitter could cause lung diseases. Pocahontas's penchant for diving off a 250-metre tall cliff would undoubtedly have led to broken bones. Aurora's infinite sleep carries the risk of heart disease. Mulan's familial pressures would have led to mental health issues, and anyone climbing up Rapunzel's hair would have likely caused her permanent hair loss and scalp damage. And finally for this week, we're looking at the mystery of the Alaska Triangle. It's a place where travellers keep disappearing, and it just happens to have the highest recorded numbers of paranormal incidents in the world. But Tim Mendham from Australian Skeptics wants to know, why are proponents of such zones so geometrically challenged? Why are they always in triangles?
The Alaska Triangle is where supposedly a lot of people have disappeared. Someone suggesting that anywhere between 500 and 2,000 mysterious disappearances a year, which is twice the national US average. A lot of wild country in Alaska, apparently a lot of bears as well. But somewhere between 500 and 2,000, so no one's really quite sure. And they say it's a consistent flow of UFO sightings. Someone puts one with the other, people mysteriously disappearing, a lot of UFO sightings, they're being taken away. And in this triangle, which is formed by joining up various known sites within Alaska, the people keep disappearing, fair enough. Someone says, some of these things that have disappeared, they actually find the bodies later on and sort of, yep, a bear. You can't say that's always going to be the case. People might just freeze to death, and it's a wild place. So my problem is that with all these things like the Bermuda Triangle, the Japan Sea Triangle, the Alaska Triangle, everyone has triangles. I think that's a bit boring. It's a geometrically challenged, I call it. No one has a horrifying hexagon or a dangerous dodecahedron.
Parallelogram.
Someone pointed out very rudely, a mathematician with obviously a typical wacky sense of humour that mathematicians have, that a dodecahedron is a three-dimensional space, whereas a triangle is two-dimensional. I think, well, UFOs up in the sky, UFOs down in the water. You really got to have a three-dimensional shape these days, to account for all these things. And triangle just doesn't do it. And often the case, like the Bermuda Triangle, a lot of the examples that are used, they never happened in the area they say they did. I think Bermuda Triangle, there were some cases raised that actually happened in the Pacific.
Well, the Gulf of Mexico anyway, yeah.
The Gulf of Mexico, there were ships, they say, heading for the Bermuda Triangle, but got nowhere near the Bermuda Triangle. That went down, that sank mysteriously, quite well known.
They were coming.
They keep shifting, so let's stick with something three-dimensional, which you can't mess around with so much. So, the dangerous dodecahedron I'm going after.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies. Or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.